In this lesson, we're going to learn how to use the key features of quadratic functions to answer real-life situations. Notice the shape as the player is launching the basketball. Notice the shape of the basketball creates a parabola. And that's what we're going to be talking about in this lesson, is projectile motion. A projectile is simply an object that rises and falls under the influence of gravity. The projectile motion is the height of that object as a function of time. So we will be finding how high an object is over a given amount of time in seconds. You can see our illustration, our graph on the right. We have the basketball that is launched. It reaches its peak, and then it comes and hits the ground. The important key features of a parabola will help answer our real-life situations. So for example, let's talk about the y-intercept. In this situation, the y-intercept starts here on the y-axis. This point represents the initial height of the basketball before it was launched. Our vertex represents the maximum height that the ball reaches and how long it takes to reach that height. Our roots represents when the ball lands on the ground, how many seconds it takes the ball to land on the ground. And in many situations, the root on the left may be negative, so it is irrelevant because we can't have negative time. So let's talk about the x-axis, which is time, our seconds, and height. It will either be feet or meters. So all of our order pairs is going to be seconds, and our output is either going to be feet or meters. So we have time is our input and our output is height. So we can see that over time, we can see how high the object is. And we can see that in many cases, we will have the height twice as the object is going up and then as it comes down. So just keep in mind when we're answering these questions of our real life situations that our input is time and our output is height. So the height depends on the time. Projectile motion involves objects that are either dropped in our first situation, thrown straight up, or thrown straight down. So we can see this is going straight up, and then a couple of seconds pass and it comes down. This one has a bit more of a curve and takes a little bit longer to come down. Here's the quadratic formula, but let's not jot this one down yet. I will let you know when you need to write the formulas. But the factors that influence the height of an object is the height in which it was dropped, whether it's upward or downward velocity is involved, and then the pull of gravity. Here are all the components. So our output, h of t, which is the height with respect to time, that is our output. A is our acceleration due to gravity, and I'll give you those values in just a minute. Then we have t. Instead of x, we're using t for time. It'll be seconds. This v sub o is our initial velocity, or the speed with respect to direction. And then our constant is going to be the initial value, the initial height of our object. So when we're dealing with gravity, we know that it's 32 feet per second squared, or if we're talking about meters, it's 9.8 meters per second squared. So in the formula, when we're dealing with feet, we are going to use negative 16. It's half of our gravity, and it's negative because our object goes up, but then it comes down, creating a parabola that turns down. So we will always have negative 16 as our A value when we're dealing with feet. Our linear term will be our velocity, and our constant term is going to be our y-intercept, the initial height in which the object begins. If we're dealing with meters, we're going to use negative 4.9 as our A value. Again, velocity is our linear value, and our constant is the initial height of the object. Make sure you get these written in your notebook. Now, let's look at this example where there is no velocity because you're simply just dropping an object. You're not throwing it. There's no force. So objects that are just dropped have no velocity. So we are not going to have a linear term. We're just going to have our quadratic term and our constant term, the initial height of which the object is dropped. And then we will have our negative 16 as our A value when we're talking about feet. When we're talking about meters of an object being dropped, our A value will be negative 4.9. We will not have the linear term, and we will have our initial height of which the object was dropped. And again, here are the formulas for when the objects are thrown. So let's take a look at our first example. Jude threw a foul shot with a release at 8 foot, approximately 20 feet per second squared. We're going to write the quadratic model as a function of time. So because we're talking about feet, we are going to use negative 16. So the height with respect to time is going to be negative 16t squared plus our velocity of 20 times time, and we begin at 5 feet. So again, our input values represent seconds. Our output value represents the height at that particular second. So the y-intercept represents the height the ball was released. And I guess we can make this a complete sentence. So right here is where we're going to get our constant. This will be our initial height. The vertex, so we have two parts of the vertex. We have the input and we have the output. So the vertex tells us two things. So let's just say t for time. So the t part of our vertex, so we have time and we have height. So the t portion of our vertex is the time it takes for the ball to reach the maximum height. The output represents the maximum height. So don't forget when you're answering these questions, if it just asks what's the maximum height, we still need to get the seconds and then plug that back into our function to get that maximum height in feet. The zeros represent, so again, our first zero is irrelevant. Our second zero represents the time it takes the ball to hit the ground. Because again, when we hit the ground, we are at 0 feet. So we're going to have some value for our time when the height of the ball is 0. It is on the ground. So now let's answer a few of these questions with our model. What is the initial height of the ball? The initial height is 5 feet. What is the maximum height of the ball? Well, the maximum is going to be right here, but we got to get the time first. So we are going to use negative b over 2a. So to get the time, negative b over 2 times a. And then let's use our calculator. So we are going to have negative 20 over negative 32. And we don't need to be rounding too much because our numbers are going to be very small because we're talking about seconds here. So when I divide this, we get 0.625. So that is seconds. So it takes this amount of seconds, not even just a little bit over half a second, to reach the maximum height. Now we're going to plug this into the function. So 0.625 squared plus 20 times 0.625 plus 5. So let's calculate this out. So we have 0.625 and we're going to square it. And then we're going to multiply it by negative 16. And then we are going to add 20 times 0.625 and then plus 5 as well. So we get 11.25. Let me make sure that that is right. Let me just put it all in one line. So a negative 16, and then we have 0.625 squared plus 20 times 0.625, and then plus 5. Yep, 11.25. So 11.25, and we're talking about feet. So the maximum height of the basketball is 11.25 feet. And it took 0.625 seconds. So now it's asking what is the height? So we're looking for the output when the ball is in the air for 1 second. So we simply just replace, again, we're going to plug in a time everywhere for t. We're going to get negative 16 plus 20 plus 5. So this gives me 25, and then we're going to subtract the 16. So that's going to be 9. So 9 feet in 1 second. How many seconds will it take to reach the maximum height? Well, guess what, guys? We just answered that here when we were finding the maximum height. So it took 0.625 seconds. So we don't have to recalculate that. How many seconds will it take the ball to land if it is an air ball? So if it doesn't hit the backboard, we want to know what this 0 is going to be. So I'm most of the time going to use the quadratic formula. So we're going to set this equal to 0, and we're going to use the quadratic formula. Negative b plus or minus the square root b squared minus 4 times a times c all over 2 times a. So let's clear this up. The plus or minus is where we get both of our roots from, and one will be a negative root because we started in the air at 0 seconds. The ball was in the air when we first began. And then we have 4 times 16 times 5. So we have a negative times a negative, so that's going to be plus. Always establish your operator over negative 32. So I'm going to just come down here and use this space. And we're going to add these together. And now let's take the square root of 720 to get a decimal. So I'm going to round here. It's 26.83281573. Let's round. Let's not round too much. So I'm going to round to the 10th though. So I'm going to have two roots, negative 20 minus 26.8 over negative 32. And we have negative 20 plus 26.8 over negative 32. So let's do this one first. We have negative 20 minus 26.8. And we're going to divide that by negative 32. So that's going to make it a positive 1.4625. And then if we do this one here, you can see that when we combine negative 20 and 26.8, we're going to get a positive, but then we divide it by that negative 32, and we get a negative value. So I get negative 0.2125. This one is irrelevant. This is what is represented here, but we can't have negative times. So any point to the left of here is irrelevant. So how many seconds will it take to land if it was an air ball? We're going to say about 1.4625 seconds. And of course, this is not exact because we did some rounding here. Then it says how many seconds will it take the ball to hit the 10-foot goal? So we want to know time when our height is 10. So I'm going to plug in 10 equals, and then we're looking for time. So we're going to use the quadratic formula again, but we have to set it equal to 0. So we're going to have to subtract out. And we're going to get negative 16t squared plus 20t minus 5. So let's use our quadratic formula again. We have negative b plus or minus the square root of 20 squared minus 4 times a. And this time our c value is negative 5 all over 2 times a. Let's clear this up. We have 400. We have a negative times a negative times a negative, so we're going to have subtract. So I'm going to multiply those values. We get 320 over negative 32. So keep track. This is where I am, guys. It's a lot of work, but that's okay. So now I'm going to come over here. I have negative 20 plus or minus the square root. When we subtract that, looks like 80 over negative 32. So we have negative 20. We're going to have a minus. So let's take the square root of 80. And we get, try that one more time. We get 8.944. So I'm going to just say 8.9. 8.9 over negative 32. We also have negative 20 plus 8.9 over negative 32. So the ball being 10 feet, we're probably going to have two real roots, because at 10 feet, it was 10 feet going up, and then it was 10 feet at some point coming down, because the height, the maximum we said was 11. So let's just say that somewhere in here and here, the ball is 10 feet. So we're going to have two different answers for our seconds. So let's calculate this. We're going to have negative 20 minus 8.9, and then divide that by the negative 32, and we get 0.9 seconds. And then let's calculate this one, negative 20 plus 8.9, and then divide that by negative 32, and we get about, I'm going to round it to 0.35 seconds. So the 0.9, this was almost a second, would be this one here. And then at 0.35 seconds, that would be here. So I have two answers here. So to hit the 10-foot goal, I would say 0.9 seconds to hit the goal, if the goal was here. But being in the air, it's in the air at 10 feet at two different times, 0.35 seconds and 0.9 seconds.